So tonight is we're going to cover a lot of material, and I know that there's a lot of stuff that this course is supposed to cover, everywhere from uh, information theory, which covers topics like database or data normalization, all the way through learning structured query language, applying it to a number of different types of uh, database engines, relational, non-relational, NoSQL. So trying to cover all of this material in one semester is a challenge at best. And it's especially challenging if you try to walk out with something more than just a survey of topics and you show up at work going, yeah, somebody told me this thing called a select statement exists. Can you show me how it works? And then they're like, so tonight we're going to cover a very large topic that one person in general was largely responsible for developing all by himself after he graduated with his PhD. I talked about some of the courses in the program out here: system science, network science, complex adaptive systems. E.F. Codd, Edgar Codd, was a student of John Holland's at University of Michigan. And his coursework and his PhD thesis was in the field of the complexity of data and information as it's formed and used in society. And it sounds a lot like a philosophy subject. And behind the scenes, it really is. When you start thinking about the philosophy of how people use and store information and share information and turn information, which is the construction of data about specific items, into learned rules about specific items. And then knowledge becomes the generalization of those rules that can be applied under a lot of different contexts. It turns into a really interesting course in philosophy and logic and the most god-awful math you've ever seen in your life when you start putting these complexity models together. So E.F. Codd developed a relational algebra for describing how information fits together in terms of its relationships from entities who are the participants in the sharing of information, and the calculus around querying that data back out so that it makes sense. But in addition, the calculus around ensuring that the data doesn't become corrupt at some point in time during these transactions as we're trying to use data. For example, it's very easy for me to sit down and say, thing A is related to thing B, and thing A is related to thing C. But if there are common items between thing B and thing C, I might accidentally say, I want this additional piece of information that's common across 5 or 6 or 7 different people or different things. And as humans, we have a bad habit of matching the first pattern that we see. So if I say, show me the person wearing the green shirt, I might point at him. But there may be other people in the classroom that have greenish shirts. So maybe I picked the wrong person by not doing an exhaustive sweep of everything. So as we start to discuss this topic of data normalization in the terms of us doing data analysis to business problems, we need to try to think about all of this work in terms of how do we prevent anomalies from occurring, not only in how we can query data back out of a system that we design and build, but to prevent anomalies in us putting data into the system, and more problematic, us modifying data that's already in a system. So maybe I create an accidental pattern and say, go update the date of birth for a person wearing a pink shirt, the person wearing the pink shirt. How many people in this room are wearing pink shirts? If you're wearing a pink shirt, raise your hand. Okay, in this light, I see no less than 1, 2, 3, 4 people who could potentially be wearing pink shirts. So it's very easy for us to create these update anomalies in practical systems, but computer systems don't really have a governor or a gauge to tell us, hey, you think you're updating one thing, but in fact, you're updating 20. Is that really what you intended to do? So there's no safety there to prevent us from potentially even corrupting a system. So we're going to talk about that tonight in infinite detail. And we're going to talk about it in terms of what it means to store data in a system, retrieve data out of a system, to represent complex data in a system, modify the data in a system, and potentially even delete the data back out of a system. So there's some minimum concepts that we need to have as we're designing and building these systems. So the first thing is, when we store data on a system, there's a presupposed concept that we're storing it so that at some point in time we could pull it back out of the system and use it in some way, shape, or form. When we were talking about the 5 B's of big data a couple of weeks ago, one of them was, what is the value of the data that we store? If we never have any intent whatsoever of retrieving the data back out of the system, why are we even worried about writing it there in the first place? So if we're writing it, we need to ensure that we can accurately retrieve the data back out, the specific data that we're interested in. To accomplish this, we need to be able to locate and retrieve any specific data item out of the system that we're interested in working with. So as we write data onto paper tape, magnetic disk, NAND-based SSDs, in the memory of the computer itself, whatever storage medium we're writing data into, we need to have some kind of a methodology that allows us to pull a single specific piece of data that we're interested in back off of that system, or even to delete that piece of information permanently off of the storage medium and recover that space. This requires that each record has some kind of a unique identifier associated with it. We refer to those as keys in general. So that ID, that record ID that we synthetically assign to a record, or some natural key information that we assign to a record, such as us when we used to use social security number to identify a specific person in a system. We have to do that to ensure that we're accessing the exact specific piece of data we're interested in. And we must also take measure to ensure that our data access and modification mechanisms are free from, or at least consider, any type of anomaly that can occur during updates. So if we think about data when we're doing our initial analysis of systems, maybe we go around the room and we take a look at the people in here, and we all have names. We probably all have some type of an identifier. The most common one that we would have in this room would be what? Student ID, the most specific ID that's common to everybody in this room. We may not all have a common type of national ID assigned to us by some type of government. Um, uh, so that would be the most specific natural key that we would operate off of in this case. So as we build a system and we think about identifying things, we have to start also considering this concept of data anomalies. So without normalizing data, without taking all of these concepts that COD put together and codified into the normal forms of data, it's likely that some type of anomaly can occur during inserts, updates, and deletes. So let's back out a little bit and think about an 800 number. So up until a couple of years ago, 800 numbers were 800 numbers. Now they are 800 and 801 numbers, and that's going to continue to change over time. But it's not really natural for us to think about people in terms of 800 numbers, is it? We think about people in terms of their names. We think about them in terms of their names coupled with gender sometimes. We think about them in terms of their name coupled with the country that they came from. In case I know two people who have the same names, but they're from different places. We even think about contexts. There's my friend Bob Smith from work versus my friend Bob Smith from church. So as we think about who we're wanting to go out and modify our bit of information about, Bob Smith got married yesterday to somebody named Sally. Well, which Bob Smith got married? I know 5 of them. So if I accidentally go out, retrieve the wrong Bob Smith record out of the database, and then update that he got married to Sally, that can lead to some very interesting Christmas parties down the road at some point in time when my wife says, "Oh, Rod said you got married." No, sorry, wrong one. Been married for years. So we have 3 basic types of anomalies that COD came up with that can exist in data modifications. The simple one is the update anomaly. Somebody gets married, you change their name. You change their last name potentially. So if you're using a natural key, a first name, middle name, last name, and you change the last name in that case, in your update statement looks something like for a record that is Mary Jane Smith, change it to Mary Jane Thomas, or change the last name to Thomas. I could potentially update too many records just being based off of Mary Jane Smith, because there's more than likely more than one Mary Jane Smith in the population of UNC Charlotte by itself, certainly in the metro area of Charlotte, North Carolina, definitely in the United States of America, and certainly throughout the world. So updates can go awry if we have an improperly conceived database system. Inserts can go awry if we have an improperly conceived database system in a couple of different ways. If we design a system assuming that any combination of first name, middle name, and last name is unique, and we try to go insert the second Mary Jane Smith into the system, it could fail, right? Can't have a second Mary Jane Smith. Go tell her parents to change her name to something else. And it looks like our high-tech video here is doing exactly what you would think it would do. So in that case, inserts may fail. They cannot be recorded because we've created some artificial constraint in our system design that doesn't really exist. The other scenario is we could end up inserting the same record that we just changed multiple times. If we don't put some type of constraint in there to say, The Mary Jane Smith that I just am trying to insert in really should have been an update of a previously entered version of Mary Jane Smith, as opposed to writing a whole new one into the system. You've got to take care in that case to prevent duplicates from occurring. And then deletion anomalies. Under certain circumstances, when you go to delete a certain record out of a system, you could potentially delete too many records out of the system. I meant to delete the Mary Jane Smith who lives on 12 Stanley Drive in Charlotte, North Carolina. Instead, I deleted all of them who live in Charlotte, North Carolina. Happens every day in real life. So these aren't problems from the 70s and the 80s and things that were solved by implementing Oracle or some other technology. These happen every day into the 21st century, and they are a matter of database system design and data architecture design, as opposed to a technology that can prevent us from encountering these things. So I talked about Cod a few moments ago. Cod was a graduate student, got his PhD, went to work for IBM, did a whole bunch of work around relational algebra, and came up with the beginnings of his data normalization techniques. And then he even invented a couple of things called R, which was the original relational database system, and a language called SQL, SEQUEL, that he had a team of researchers at IBM working on. The challenge with it was IBM sold mainframes. IBM sold mainframes that ran their proprietary IMS database system. They made amazing amounts of money off of it. And they viewed everything that Cod was coming up with as a mechanism to destroy this giant cash cow that they had built that relied on big, heavy, big iron machines to run. So they gave him a set of graduate students, effectively, and engineers at IBM. They sort of kind of hacked up a version of a relational database system running on a mainframe. And even the badly implemented, horribly designed, poorly implemented system ran circles completely around IMS. It was so much easier to use. It was so much more efficient. It was so much more high performance that it was obvious that this was going to become the technology of the future in terms of database management systems. So IBM continued to push it behind the door. They didn't really sell R or SQL as a product unless somebody specifically came asking for it. He started to work with a guy named Christopher Date, or CJ Date, at IBM as well, kind of crafting together more of this relational algebra construct, the relational database management system engine. He went to a couple of what was the things we used to have in person that we don't have anymore. Starts with a C. I can't remember the name now, but there were conferences. That's the word we're looking for. Went to some conferences, showed a whole bunch of people. Everybody got really interested in it. And there was a guy in the audience named Larry J. Ellison. And Larry saw this and was like, oh, dear God, this is exactly what I need to take and build a product off of. So he built the very first version of Oracle for who? Who would want a really good database, really, really fast, that could sift through information at light speed in the 70s and the 80s? The CIA. So the very first people who ever deployed Oracle was the CIA and the NSA, National Security Agency. Oracle 3, 4, 5, if you didn't work for the NSA, the Department of the Navy, or the CIA, you never even knew it existed. After which, the first commercial version of Oracle version 7. He had pretty well implemented the relational database management engine at that point in time, and was selling it commercially. And that's why Oracle has such a footprint in corporate America now, is that they've just been doing it so long. It's not necessarily that their product is the thing. They're just embedded everywhere because they've been doing it so long. So if IBM had taken the lead and started developing the product instead of letting Larry Ellison build an empire around it, the entire software market as we know it right now would probably look completely different than it does. So many of Dates and Codd's theories developed in the 60s and 70s are still implemented exactly today as they were 40, 50 years ago. That's pretty interesting, isn't it? That some technology, some theories are so well founded in their initial form that they survive completely intact. And that's why normalization is such an interesting topic to address. You never get it right the first time, but they did. So a couple of bits of prologue we need to go over up front. Everything in the language of describing data normalization is written around a few things. One of them is called a super key. Well, what the hell is a super key? That sounds like a made up word, and it is a made up word. But basically what happens when you're looking at a collection of data, it doesn't have to be arranged in any way, shape, or form. But if you're trying to collect a bunch of data together, you're trying to figure out, how do I identify in a one-to-one mapping a set of keys or a set of elements out of these keys or a set of attributes out of these records that uniquely identifies a row in that database. So the most trivial super key in a database is every column or every attribute associated with a record. I've got 700 attributes, all 700 of them, as long as there aren't duplicates in the table, each combination of every possible attribute is a super key. But that's kind of useless. That's like saying for every person on the planet, what we're going to do is take their entire DNA and use that as our key to identify Rob or Tom or Jerry or whoever. It's impossible to use. I need to go pull up Rob's employment record. Okay, Rob, give me a DNA sample. We'll sequence it, then feed that into the relational database management system. And in 3 to 7 weeks, we'll be able to return your record out of the database. So what we want to do is figure out how to find other possible super keys that lead to this functional identification of a row in a table. What's the mathematical definition of a function? Because that's what they mean when they say functional dependency here. A functional dependency in mathematical terms is nothing more than something that maps an input parameter to exactly one output parameter. So in doing that, we come up with one or more elements that will get us back one specific entry in this table. And I know this is kind of hard to read. This is social security number, last name, first name, middle name, date of birth, pet's name, and pet type. So 111-11-1111 stands for John Reuben Smith, born on March 23rd of 1953. He has a pet named Zoe that is a dog. A lot of different information in this row of data. At this point in time, we're not trying to make a whole lot of sense out of organizing the data. What we're trying to do is figure out, how do I pull back one particular person's bits of information and ensure that I don't accidentally get somebody else's in that mapping. So just looking at this data, there's any number, or the small set of data, there's any number of ways I can do that. So the first thing we do is sit down and figure out, what are all of the sets of attributes in the system for these particular sets of data. So I start off doing this mapping of, well, one set is just the attribute Social Security number. The next set is Social Security number and last name. The next set is SSN and first name, blah, 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 so and so and such and such. And those are all the first and second order attributes. Then I can go to the combinations of third, so on and so forth, until I get all the way out to all 7 columns of this thing. That seems like a lot of work, and it is. It's not necessarily important to do that, but we do need to at least sit down and go through some type of exercise around, what are the things that uniquely identify a tuple? And to do that, we take all of these combinations that we come up with, and then we go through and eliminate all the sets that do not uniquely identify a tuple. So instead of mapping out every single possible combination of every attribute out there, we sit down and we apply a lot of brain power to this and say, okay, so in and of itself, last name probably isn't going to uniquely identify a person on planet Earth. Lots of overlap there. Neither is first name, neither is middle name. Neither is date of birth by itself. Neither is pets' names. Probably a lot of people have a cat named Scratches. Maybe, I don't know. Maybe nobody does. But in theory, multiple people could have a cat named Scratches, therefore it ain't a candidate in this case. Pet type, if only one person on the planet had an alpaca and only one person on the planet had a cat and only one person on the planet had a dog, probably be a decent, unique, functional map, but that's not true either. So other than Social Security number in this case, we can logically just eliminate everything by itself. Then we start to get into more detailed versions. We know that last name's not unique by itself. Last name and first name's probably not unique by itself. Last name, first name, and middle name, is that maybe unique by itself in our world that we work in this classroom? Last name, first name, and middle name is enough to be unique. And that's where we start to typically go off the rails in database design, because we think about the data that we're presented with. We don't think about what could happen over space and time as we bring in new employees and things like that. At some point in the future, is it possible that we could end up with 2 or more employees that have the same combination of last name, first name, and middle name? Yes, that 3-tuple candidate is out now. What about last name, first name, middle name, and date of birth combined together? We did that for a very, very long time, and it worked very, very, very well, until more and more people started populating the planet Earth. Companies got bigger, and suddenly people with the same first name, last name, and middle name, born over a lot of different regions, started to have the same dates of birth. So the 4-tuple there doesn't work either. So what we end up out of this is the only logical super key we have on this page is Social Security number, because it's a synthetic number as opposed to some combination of things. So you don't really have to go through all of the 3 steps there. you need to sit down with at least one other person who also has the domain knowledge you have and sit down and figure out what the actual possible super keys are for a piece of data that you're working on. And you're still going to end up with problems in that. In this one case, what do we assume? People only have one pet. How does somebody have more than one pet? You put a duplicate row in there for Social Security number 111111111. So it says that John Smith also has a cat named Satan. So now you got a bigger problem in that Social Security number is no longer a functional relationship such that it returns exactly one row of data out of this table. So you have to, data architecture is very much an art form that's also strongly coupled with a science. So that's probably what makes it such a fun career to do, is coming up with the optimal way to store and identify data is just, you know, a very compelling thing. Let me check comments real quick just to make sure there aren't any, since I don't have everything up, and there aren't. Good. Okay, so if we continue out our exercise from just a moment ago, we have all of our different one combinations of attributes, two combinations of attributes, three combinations of attributes. For an entity with n attributes, there are the sum of I equals 1 to n factorial over r factorial, the quantity r factorial minus n factorial, or excuse me, n factorial minus r factorial, sets of attributes from which to select superkeys. Basically, every n combinatoric between one field and the total number of fields in that data set is the number of possible entity combinations you would have to sit there and sift through if you didn't apply semantic analysis of the attributes that you're working with. Understand what the domains are as opposed to looking at what the values are in a particular arrangement. So if you tried to build a spreadsheet around this, you'd be doing it forever. I mean, I got so annoyed just putting parts of this PowerPoint slide together. I can't imagine trying to do it in real life. So your super key selection then results back to taking each one of those attribute sets and eliminating any that do not uniquely identify a row in the data set. So we talked through this just a few minutes ago, and I went through and removed the 1 and 2 combinations that weren't unique. But what I ended up with was a 2 combination of SSN and last name, SSN and first name, SSN and middle name, SSN and DOB. I took out pet's name and pet's type. Why did I remove those? Pets can die. That's part of it. The other part of it is you can have more than one pet. So you don't have your functional dependency there when you have a one-to-many relationship inside the data. But these are partial key dependencies in here. If SSN in and of itself is a proper, unique way to identify a single human being on a planet, SSN, along with any other element in that row of data, is also a possible unique way to identify any other person on a planet, which is why a super key of every element in the table is a potentially valid super key. But all of these other last name, first name, last name, whatever, they're all out. Yeah.
Like what's the justification for using 2 combinations?
So we're going to get into that when we start getting into second and third and voice cod normal form. There are some specific cases when you start to define child tables where you end up with combinations of elements as keys in there. And what you find out is in certain cases, they're also bad decisions as well. But if you understand the possibility of the types of errors you can come up with, maybe you will allow a composite key in that case to be used. But most times you just completely get rid of composite keys and replace them with a singular synthetic key. So we select our candidate keys. Candidate keys are keys that are super keys, but they are a minimal representation of an identifier to pull a record out of a table. So going back to our multi-part keys we were just looking at, SSN, SSN last name, SSN first name, SSN middle name, SSN DOB, SSN last name and first name, SSN last name, first name, middle name, blah, 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 so and so and such forth. Because this one has the minimal number of elements to it, and it is just as selective as any of these multi-part keys, we select it as the candidate key out of the set of data that we're working with. So we end up with a very small, very compact, very descriptive identifier to use as the key for insertion, update, and deletion of data out of our system. Any questions on anything that I've talked to up to this point? And secondly, how much of this is not new to any of you in this class? Have y'all covered normalization before anywhere else? Okay, cool. So I can make up anything I want to. Last time we met, we talked a little bit about the concept of synthetic keys. So one thing that is easy to do, you can ensure a one-to-one functional dependency between your key and your data if you arbitrarily assign a unique key value to every unique row of data in your database, irrespective of what the content of that row of data is. So the concept of synthetic keys is it allows us to create some type of universally unique identifier or monotonically increasing integer value that we attach to each row of data in the database. So the reason we do this is if we go back and think about our candidate keys on the previous table, what happens if we don't have this SSN synthetic system assigned value in there to identify individual people in a row in a table? What does the key have to start looking like then to specifically identify you versus you versus you? I'm sorry. Larger sets, but let's have a little conversation about how ludicrous that gets really quickly. First name, last name, middle name, parents' names, full names, where you were born, when you were born. What is that even unique? I mean, so my great grandfather came here from Italy back in the 1800s. And I came from a very poor family. So poor families don't keep good records at all in general. So I started doing the genealogy thing, and I somehow managed to track my great grandfather back to this little town of Arco in Trentino, which was part of Austria at the time. It's part of Italy now. And his name was Luigi Boni. No middle names. God help you, there's no middle names. So guess what one of the most common Italian first names is? Luigi. Great. Any guesses as what Luigi's daddy's name was? Luigi. What was his mother's name? Any guesses? Maria. Hundreds and hundreds of Luigis and Marias had hundreds and hundreds of Luigi Bonis as children in the same year, every year. So even though I knew his birth date, I could only get it down to about 30 people who just happened to be born on the same day named Luigi Boni, whose parents were Luigi and Maria Boni. So without the concept of being able to identify from first principles some fingerprint that I can put on a record, the concept of a key to identify a single individual human gets ridiculous very, very, very quickly. So when we go through the process of entering a person into a system, and a human being does all of the vetting out to figure out person A named Luigi Boni is really truly different than person B named Luigi Boni, and the system assigns them a new identifier that they then know and pass along when somebody says, "Who are you?" "I'm Luigi Boni and my social security number is 111-222-3333." You have that synthetic key as an aid to help you pick out the right record. So the concept of a synthetic key is very important in terms of sufficiently and efficiently identifying a specific person in a database. But once again, what if we don't use a synthetic key? What happens? What happens when Maria De Filippi married Luigi Boni and became Maria Boni instead of Maria De Filippi? Well, if we don't have a synthetic key and all we have are last name, first names, and middle names, and I go out and I flip somebody from having a last name of De Filippi to Boni, and I potentially pick the wrong one because God knows they all have the same names, it's very easy for me to corrupt my entire data structure in the database without this concept of a synthetic key. So it's very important for ensuring data integrity. It's also very important for efficiency to search through this table and find the person that I'm looking for with certainty. And it's also very inefficient on the person who has to fill out 600 key fields on a user interface somewhere and then press the find button only to come back and find out, oh dear God, there's still 34 people and I don't know which one's really the right one. I quit. So and that was basically the end of my search towards my family history at that point in time. So database systems very early on came up with a concept of creating and generating synthetic keys for new rows inserted into tables. Sybase and later on Microsoft SQL Server came up with the identity property, which basically allows you to assign that property to a key value, and it consistently sits there and either adds 1 or 100 or 50 or whatever the step value that you create. By default, it's 1 to every new record inserted into the table. Oracle has always had a sequence object that basically does the same thing. You go and get the next value from a named sequence of numbers, and you physically use that as part of your key when you do the insert into the database. And then we can also use other schemes such as universally unique identifiers. You've seen these things. Those numbers that look like F6EB-2647-473J92- whatever. Microsoft uses them everywhere and calls them GUIDs, or globally unique identifiers. But they're used in a lot of different places, and they're fairly consistently unique over space and time. They're not perfect, but they're fairly uniquely consistent over space and time. The universally unique identifier, or the UUID standard, is a NIST, or National Institute of Standard and Technologies, mechanism for computing unique numbers. But even then, their go-to is, before you assume it's a purely unique key, go and see if it's already in the database or not, and then generate another unique one until you get one that's not in your database, and then that becomes the unique key. So synthetic keys are very, very useful in our systems. Byword on that, keys that are very big and very large, whether they're large concatenated multi-part keys, or whether they're really big strings like GUIDs or UUIDs, they make really horrible indexes for pretty much every database system on the planet. They're very inefficient in terms of memory storage, and they're also very, very inefficient in terms of the searching algorithms that you use on very large strings. So even though it might sound like a very cool idea to use a GUID or a UUID for a primary key on a table, just don't do it. It's don't do it. Don't. So Cod came up with his set of normal forms, and the first ones that he came up with are the unnormalized form, the first normal form, the second normal form, the third normal form. And then later on, he worked with a gentleman named Boyce, who identified a slight little nuance in third normal form that could result in an anomaly under some fairly weird situations. So they created an addendum to third normal form called Boyce-Codd normal form. In almost every case, you will only, for practical purposes, take a table to third normal form when you're designing it. You will occasionally run into that weird, odd nuance that requires you to take it to Boyce-Codd normal form. But for all intents and purposes, a table in third normal form is also in Boyce-Codd normal form by default. So unnormalized form, or UNF, is the easy one. Basically, all records in a system must be identified by some kind of unique key. We don't care about what all of the attributes are in the record. We don't care if they violate every piece of relational consistency in the world, as long as for all combinations of attributes in a record, there's exactly one of them in this table, and it has a key associated with it to uniquely pull up that big, long record by itself. When people used to build mainframe database systems, and I say that like they don't do that anymore, but they do, you ended up with just gigantic chunks of stuff written into big, long rows and flat disk tables in COBOL. And you would go through and create indexes off of those. But in the end of the day, you would go back and say, go get me this gigantic, massive record off and load it into memory, and let's play with it some. So you would end up with things like an employee's name in a table, along with their birth date and all of their family members in a column, and their addresses spread throughout this thing, and their phone numbers, and where they worked and the office number they worked in and stuff like that, all in one big row. And the reason you could do that is it's very, very efficient on a mainframe to go out and just grab a big chunk of data and load it into memory. And it still is today. So the bit with this is having a key makes it possible to access any record off of storage very quickly and efficiently. Each new record written in the system must have a new unique key value that doesn't exist in the system already. Any updates made to an existing record must be written to storage using the same key value that was used to retrieve it. So if I go out and pull back Maria De Filippi's person record and change her last name to Boney, when I write it back in, I need to write it back in using that ID so that it overlays the data that was there before. Told y'all this was a lot of coffee. Y'all should have gotten your coffee, but you didn't get your coffee. So once again, this presupposes that our data access mechanisms can go out and locate a specific record off of our storage system, can rewrite a record back over the top of it, and it can also enforce the uniqueness and integrity of key values throughout the system so that I don't write the same key value multiple times into a file. So that becomes very easy when you have a lot of different people accessing and using data out of a system, because in a split second, I go get the next value and you go get the next value. And if we're using some cheesy mechanism to do that, it's potential that we both end up getting the same value because value 12 isn't in the table yet. So it's like, go get the biggest value that's not already in the table, 12. Go get the biggest value that's not already in the table, 12. Both of us write 12 in at the same point in time. Now, voila, there's two record 12s in the system. If there's nothing out there that says when the second write of 12 goes out there, 12 already in the table, yep, you lose, go get you another value. And you keep going and getting another value until you finally get one that's not written in the table. Well, that sounds pretty stupid too, doesn't it? That's why this whole concept of an identity property that is assigned at the time that the data is written into the data structure, or in the case of Oracle, the concept of a sequence object, which is basically a critical section that says, at this point in time, only one person can access it. Yusuf goes out and gets the next employee number. Now I have access it and I get the next employee number. So there's these locks and wait states and everything else that prevent duplications from occurring. So you almost have to have these concepts engineered into your database management system, because trying to write them into the program that a user is running is too far from the data storage engine to do it efficiently and do it without error. And we're back to unnormalized form. So there's 9 slides left, and we're going to be lucky to finish them by the end of this session tonight. And the issue with it is taking data from an unnormalized form state where all you really know that you have is a key to identify a particular entity in the system, into a system that the data is arranged in a mechanism that will prevent the insert, update, and delete anomalies, as well as provide you a mechanism for querying that data in an efficient manner, is difficult. And it's difficult in a lot of ways. It's difficult in that you have to go through and address every attribute and set of attributes in every row of the table and determine whether or not they belong in that table, whether they belong in a different table, or whether they belong in an entire data organization strategy of itself. And it's also hard at the same time because there's no one right answer almost ever. So when you sit down and you come up with a data architecture for a system, it's right as long as you and your business partners who own the problems and some of your peer architects and your system engineers and your database engineers who are responsible for making this thing perform in such a way that it's usable as the system scales up. That's more of what makes it right than following 5 sets of rules to get this thing from unnormalized form into Boyce Codd normal form, because you can have a database where every entity in there is in Boyce Codd normal form, but it's wrong because it's not performant. It takes too much hardware to run it for the amount of data that you have in it, and it is too slow because it has to knit all of these complex relationships back together to produce a record on a screen. Question? Okay. So our first journey into this is to get from unnormalized form into first normal form. And there's a little piece of doggerel that came out in the 80s associated with the first 3 steps of normalization that says that all data must depend upon the key, the whole key, and nothing but the key, so help me Codd. So that's basically a walk from unnormalized form to third normal form in our system. So our first step in this process is, first thing, we've got to make sure that all of the data in a tuple in this record depends on nothing but the key itself. So the simple definition of that is all attributes must be functionally dependent upon the primary key, which means that for any attribute in this record, there needs to be a one-to-one correlation. So no repeating groups inside of a single column or attribute in the table. So no table-based columns, no comma delimited lists being stored in a single attribute, things like that. So if we look at this microscopic piece of overhead up here, our first column is employee ID, which is a synthetic number. Last name, first name, middle name, birth date, and then this column called dependents. And dependents in our 3 sample rows has 3 different types of entries in it. The first entry for employee ID 1 is null, meaning that they have no kids, or at least no kids that the company is aware of. The second is where the employee has a single dependent or child named Mary. And the third row is where this thing comes out of the blue and nobody anticipated of, oh my God, this person had 4 kids, but we've only got 1 column to store dependents in. So I got an idea. Why don't we shove them all in the dependents column and we'll separate them by semicolons? That'll make everything perfect. So you see a lot of this in old mainframe systems where there's no real necessity to identify a different way of storing the data. But how can this go wrong really quickly? So what I want to find somebody who has a maybe a employee who has 2 or more children. All employees who have 2 or more children. So, well, not knowing any better, Maybe I go out and say if there are more than two names in the dependents column, but now I've got to write an interesting little piece of code that goes through and says if there are semicolons in that value, then go through and parse every piece of data separated by a semicolon and count them up. And if it's two or more, return that employee ID. Very inefficient in terms of how you write that query. And it also requires somebody to do a lot more than write a simple select statement to pull it out. It also potentially allows me to create some problems in there where I go in and say, oh, guess what? James Seaborn Thomas, who's employee ID 3, just had another child. It's pretty easy for me to accidentally blow away his first 4 children and write the new child's name in the dependents column if I don't write a specific set of logic that says go through, find the last child, append the string onto it, put that string back into that data element, and then go write record ID 3 back onto the whatever storage medium I'm writing to. So these kinds of things caused all kinds of issues. So the first thing that we try to address in the normalization framework is to get rid of these repeating values or these repeating groups as attributes inside of our system. And we do that by any number of different ways that can get convoluted, even for something as simple as this. So the way I broke this out was instead of having a column for dependents in there, I created a child table called employee dependents. And that's a one-to-many relationship because an employee can have 0 or more children, as we saw from our test record, where employee ID 1 had a null. Now employee ID 1 just doesn't have an entry in the employee dependents table. And then in the employee dependents table, we have an employee ID. So employee ID 2 has a single child, dependent ID 1, a synthetic key, monotonically increasing, starts at 1, next one's 2, next one's 3, next one's 4, next one's 5. And he has a dependent name of Mary. Then employee ID 3 has 4 kids, each one in sequence in this employee dependence problem, or this employee dependence table. So this gets rid of the repeating groups challenge and allows us to get the employees table into first normal form. But this isn't a perfect solution either. Any thoughts as to why it might not be a perfect solution or necessarily even a good solution? That's part of it. This is now a potential partial key dependency. The primary key for this child is the dependent ID. So Mary's ID is 1. It's not necessarily dependent upon employee ID at all. And this, quite frankly, is the case that causes third normal form to require the Boyce-Codd normalization strategy, which we'll talk about in detail when we get there in just a little bit. So this is the pathological case in third normal form where we end up with a reverse functional dependency between the two of them. But what's a more simple, pragmatic approach that causes this to be bad? I'm sorry? It's not that it's in 2 different locations, but there's the potential for 2 different somethings. This is a big company. Over space and time, what kinds of people could work there? Spouses. So in that case, let's say that employee ID number 4 is Reginald Eugene Smith's wife. who is also a parent, or excuse me, Daniel Jordan Travers' wife, who is also a parent of Mary. So if I bury employee ID in here, now I've got 0004 dependent ID what? 0001, which is a duplicate now that refers to the same person, Mary. So is this good enough or not? Well, we've got a policy that says that spouses can't work at the company. So we'll stick with this until somebody sues the hell out of us and says we have to hire their wife, and then we're back to step one of tearing the system back apart to fixing this. So that's why you can't, and you'll see this in the book a lot, and you'll see it in a lot of places. You can't make decisions on whether your normalization strategy is correct or not just by looking at the example data that you have. You have to consider what are the possible things that could happen over space and time with employee situations you've never seen before. Think about, and this is a very real problem. Think about all of the systems that were written prior to the turn of this century where a spouse was either male or female. And if one was male, the other one had to be female. That has caused ridiculous amounts of expense to be incurred, going back and changing something as simple as it never really mattered in the first place. But by God, we stored it in an attribute somewhere and it started breaking business logic. So there's lots of things that you need to take out of the equation when you're defining the relational algebra that relates records together. So other ways around this. So I started off with just an employees table that had a employee dependence table, but I could also have the concept of everybody is a person, and a person is either an employed person at the company or they're a dependent person. And then an employee has dependents. So when I talk about somebody having a job and they're working in a particular office or something like that, I refer to employed persons records in that entity. But if I want to know if a person has children or not, I can take employed persons, go through this employee dependence association table and find the children or the other dependents that they might have for HR and benefits purposes. So now I've created this interesting circular dependency here. But this even has a problem. And why does this have a problem? This has a problem because I assume that a dependent is the dependent of an employee in this case. I'm not just tracking it from the fact that it's a person and then this is a dependent of a person, they're dependent of an employee. If they change jobs and go work at another company, or are my kids no longer my kids? They still are. So why would I model this using an employee ID to determine who my kids are as opposed to using a person ID? So maybe I rewrite it a little bit differently so that I've got persons in general, and a person can either be a guardian or a person can be a dependent. And then there are these guardianships, relationships set up that says that Rob is a guardian of Jane and my wife Sherry is also a guardian of Jane. And we can both now work for the company because persons is what the employee relationship is set up around. And if I retire or quit or whatever, this dependency relationship all still works perfectly fine for the purposes of employee benefits in case I retire. I'm no longer an employee, but I can still get benefits for myself and my spouse and my other legal dependents if necessary, without having to come up with some weird representation of a person still being an employee of a company or not. The other reason I might want to do something like this is, what just as spouses might work for a company, what else could happen? Some point down the road, if I stay there long enough, my 14-year-old kid could become an 18-year-old kid and start working for the company as well. So in that case, this dependency or guardianship relationship ends on some date when they turn the age of majority or disown me or whatever and go get their independent status. There's a term for that. What is it when kids sues the court so that their parents are no longer their parents? Emancipation, that's it. They become emancipated children, and then my child can go to work for the company that I work for and become my boss and fire me. So, so this guardianship relationship might end at some point in time. And then that person who is my child could also become an employee of the company. Unless you're doing HR and benefits and all sorts of other stuff, you don't necessarily have to tear the relationships down to this level of detail. And that's why it goes back to what I said earlier. As long as you and all of your groups of friends sit down and agree that we've gotten this to the right level of granularity, that's where you stop. Because we could continue to tear this down and make it deeper and deeper and deeper and cover all sorts of stuff that's never going to actually be a problem at the company we work at, but it would be a really cool thing to do and beat up a lot of time doing it. So now we're at first normal form, and it's 6:57. So second normal form, to go to the next stanza, depending on the key, the whole key. This gets rid of partial key dependencies in the data set. And I've got two of those outlined in red in this particular situation. And you can argue there's more here. I'm going to go with these two specifically. So in our employee record that contains name, addresses, postal code, phone numbers, there's a block of data for job title, and then there's a block of data for work location and the mail stop or office number that I work in as an employee. So are these values strictly dependent upon the key of this record? Is my job title dependent upon my employee ID? Is the work location and office that I work in strictly dependent upon my employee ID? We get some clues looking at the data here. And the clue is that these job title values repeat over multiple rows inside of the data set. So does my work location. My mail stop or office number doesn't necessarily repeat, but why would I consider it to be related as one group of data that's not dependent on employee ID? What about this office number makes it not dependent on employee ID, but dependent on something else?
People can work in the office, or you can change offices.
You could change offices so the office isn't specific to a single individual, but the mail stop exists in this building. If I move to a different building, I'm not taking the mail stop with me. So because the mail stop is dependent upon the work location, that's a different key dependency than the employee. But you're exactly right. if the employee was terminated or transferred, the work location and mail stop would continue to exist just as if Rob was never there. So after my kid fires me, somebody else moves into my office and they throw some type of party. Same's true of job title in that case. There are multiple people who have the job title field engineer in this case. So me quitting or me moving on to something else does not cause the job title field engineer to go away. So it is its own domain of data in this case, and therefore gets its own entity in turn. So the purpose of this is to identify things that are in this record that aren't in the employee domain, but are really in other domains unto themselves, and creating entities to store them and relationships to associate those entities together. So I'm sure you can see this. Let me see if there's a way to fix this. My guess is no. Let me try doing something. Try dragging this over here. Oh, stop it. And zooming in maybe. All right. So, like I said, we took our employee record and we identified job titles as a set of values to work from. And we also identified that work locations and the offices inside of those work locations were individuals, entities unto themselves. Sure, I'm just breaking this thing all over the place. So the first thing that we do to take this thing into second normal form all by itself is to take out the non-functionally dependent values out of the tables. So they're gone. Absolutely removed them from the employee table altogether. And I've created new entities. I've created a job titles entity, which contains an ID synthetic key and the job titles that we saw. And it would contain many more, right? Because there's got to be more than a field engineer too, and an engineering manager in a company. I also had a work location and a mail stop column over here that I got rid of. So mail stops or offices belong to specific work locations. So this Caulfield 1 work location gets its own record with its own synthetic key. So I can uniquely identify each row in here. And then each office inside of Caulfield gets its own synthetic key and a mail stop name associated with the value that used to be inside my employee record. So when I assign this back to an employee, I don't necessarily want to associate the employee with both the work location and the mail stop ID they work in, because then I've got this partial key dependency again going on between two different entities if I also drew a line over to here. However, by creating this, what is actually employee locations table with a relationship value between employee ID and mail stop ID, I can identify the specific office that the employee works in, and then I can use that mail stop ID to go back up a level because of this relationship here to figure out that mail stop NJ1C231 actually lives inside of Caulfield, New Jersey. So I don't have to put every detailed piece of element in the child record. I can use these relationships, this one-to-one relationship going that direction, to identify what building a particular employee works in. So this gets me these association tables, employee locations and employee titles, breaks that non-functional dependency from entity to entity and allows me to take the data out of the parent entity itself. So this is something that you're only going to get comfortable with playing with it over time. And we're going to continue to tear apart this big, scary robots business case over the rest of this semester, putting together an ER diagram and a relational database model for these things. And it'll be interesting to see what everybody comes up with as all of their different rationales and variations and way of doing things, because like I said, there's no one right answer to any of this. It's only wrong if it doesn't enable you to solve the problem you're trying to solve. Yeah.
Does the other address not, or like you said, oversight form, is this dependent on the employee itself, even though like New Jersey and
So the mailing address doesn't violate second normal form. It's going to violate something in the very near future. So, yeah.
Is there a reason that we couldn't use MailStop name as the primary key instead of making MailStop ID? Is it just
No, so there's let me put it back up on display. Not necessarily. No, the challenge with it, instead of creating a MailStop ID as a synthetic number, let's say that we brought in a consulting company and they decided, oh, you need to regrid your buildings. So now it's not NJ1C211, it's NJ-01-25- something else -211. You're not supposed to ever change the values of primary keys because you could potentially screw up.
Yeah, that makes sense.
Yeah, so that's really the only reason you would use an ID versus the actual value itself. And we're gonna play hell with that on the next slide with zip codes. Third normal form, the last part, the key, the whole key, and nothing but the key. So to where you were just going with that, we've got the remainder of our problematic data here of mailing addresses, home phones, and mobile phone numbers. What have we already talked about? What condition that we've already talked about potentially makes mailing address violate our normalized data forms sitting in this table, potentially even second normal form? Two people who live in the same address and have the same mailing address. So potentially this violates second normal form, just having mailing address in there. But it definitely violates third normal form because this data, this mailing address, is in no way, shape, or form functionally dependent upon employee ID. I may have had the mailing address before I ever went to work for Big Scary Robots. I may change my mailing address at any point in time. I may have multiple mailing addresses. Bank of America, I had at least one in Charlotte and one in Alabama for almost 10 years. So you can't necessarily say that an address is functionally dependent on an employee name, but we come up with this weird phrase, all non-prime attributes must be non-transitively dependent upon the primary key. So here's your weird situation on where that comes out to. It's not necessarily the entire mailing address by itself that's a problem. It's every single attribute of the mailing address that's a problem. So I've got a street address, maybe an apartment at a particular street address in a city, in a particular state with a postal code of 08096. Zip codes change over time in the United States, and they probably do in other countries as well. So I can't include something here that is functionally dependent on an employee ID and a street address and a city and a state to tell me what particular postal code I'm working on, when in fact this postal code in and of itself at any given point in time is only dependent upon the mailing address, the city, and the state. So I'm pretending that as a function of A and B, I get C, when in fact, C is really only dependent upon this combination of fields that we refer to as B here. So you lose the backwards computability trying to make that transitive statement. And you end up with something similar when you start talking about phone numbers. Area codes change. This phone number is not necessarily back 20 years ago dependent upon my employee ID. It was dependent mostly upon the city and state where I was located in. Now it's not dependent upon that anywhere. How many people's cell phone numbers actually match the area code anywhere in Charlotte right now? I know mine doesn't. I haven't had a cell phone number for probably 15 years that matched the area code of where I was. So you can't include these types of partial dependencies inside of a table and have the table be in third normal form. So you have to go back and not only take all of these elements out of the table, but you also have to create new structures for these things to make them functionally correct. So let's look at what that might look like for just a moment. And I will break this out and zoom it in over on the other monitor. All right, so I took the employees table initially. I didn't do this with the phone numbers because we can do that another way, but I wanted to go ahead and do it with addresses and stuff because that was kind of the first big problem we looked at. So we've got addresses. So our first address that we had, 2315 Park Slope Drive, Woodbury, New Jersey, 08096. So in this case, if we had multiple employees who both lived at 2315 Park Slope Drive in Woodbury, New Jersey, we would be able to use an association table, an employee addresses table, to link a specific employee to a specific address. And we could put any number of employees in this table and have them linked back to that specific address. And that's the whole purpose of an association table, is that for any row in this table, all you have is a primary key in an association table. However many columns are in that association table is the entire primary key of that table. So there are no unfilled functional dependencies because the entire key is every attribute in the table. It's also functionally accurate going back because this ends up being a one-to-one relationship because every record in this table matches exactly one record in the parent table. That's why if you look at the crow's feet on each one of these association tables, from parent to child, it's 1 to 0 or more. An employee can have 0, 1 or more employee work locations that they potentially work at. But any employee in this record is always Rob Abbott or Tom Smith or Jim Jones or whoever. And it's the same going the other way. For a particular mail stopper office that employee works in, it refers to exactly one specific location. So that's why you have to break up the many-to-many relationships in this case where an employee might work in multiple locations. You have to be able to identify every single specific unique location that employee works at. Yes?
Is there any reason why work location ID is left off of work location outside? Would that not be their column there?
So it in practicality, it would be. When you draw these maps out and you show that there is a parent to child relationship, it assumes that once you actually build the table, this ID will come down and become an element when you build the physical data model. So these things become wider at some point in the future, but as long as they're functionally dependent, they don't violate any of the reasons that we've been taking them out from the other side. So you have the same thing over here. Address ID is here because of the parent-child relationship for the same exact reason. The same thing would happen here, and the same thing would happen there. So if you looked at mail stop ID being a child, mail stop ID being a primary key of work location mail stops, and employee locations being over here, what's potentially going to happen? This in and of itself is the minimal primary key in this table. Me including work location ID and mail stop ID and sending it over here is no more prescriptive because this is a unique key value. So even though this foreign key is going to get embedded in this table, I don't have to bring it over there because mail stop ID in and of itself is a unique singular key with one attribute. I could definitely embed it over there, and there's nothing wrong with doing that. It's just slightly less efficient in terms of data storage. So it's not, once again, it's not wrong. It's just whether everybody agrees we embed keys all the way across or we use the minimal key.
Or that foreign key of the parent associated to the primary key of the child. Everything.
Say that one more time.
So say for the work locations, you have primary key and from the work locations, you have another primary key. But you,
Yep.
But you need to relate these two entities. One of the entities is going to have foreign key, right?
Yep. Yep.
In situations, we select primary key as our primary, or we select foreign key as our primary key.
So the only consideration you make in this case goes back to the concept of what is the minimal key necessary. There's nothing wrong with me saying that a combination of the foreign key and this increasing synthetic key here is the primary key. You could definitely do that. It's just a matter of whether you want to or not. As long as you have this unique value in and of itself that identifies every row in this table, you don't have to include the foreign key as part of the primary key, but you can. And there's reasons you might want to, and here's why. Let's say that I wanted to very quickly identify all of the mail stops at a particular work location. So if my primary key in this table was a combination of work location ID and mail stop ID, I don't have to actually join back against this table to necessarily identify a particular location associated with a mail stop ID. I can just simply go through and say anything with a work location ID of 001 in my where clause, plus any mail stop ID associated with it. Now I've got the list of every location in Caulfield without having to necessarily do a join. So sometimes concatenating foreign keys into a primary key can make your queries a lot more efficient. So even though it doesn't meet that criteria of minimal primary key anymore, it aids in performance. So sometimes you will make a decision to not necessarily normalize a table all the way for performance reasons, because maybe the use of that data is for reporting rather than for transaction processing. So in doing that, it's read only principally. So there are no insert, update, and deletion anomalies. So if I want to put it in first normal form and it performs better that way, depends on what solves my problem the best.
Right. You mentioned about the minimal primary key in the database.
Yep.
Model, let's say. The work locations ID, say we have mail stop ID, the primary key, as an example. Work locations ID in this example is also the primary key, although it's a synthetic key, right?
It's a synthetic key.
Yeah.
Yep. And it's a foreign key in this case because it links a particular mail stop back to a particular building effectively.
But the work locations ID is a primary for, isn't that a primary key for that entity itself?
No, because in case of a mail stop, all we're talking about is offices. We're not talking about buildings and the offices in them. We're talking about offices. So when I've got an office, I can relate an office back to a building that it's located in. But if I put all of this together, Caulfield as the work location and mail stop in the same table, what I'd end up with again is Caulfield 1, NJ1, blah, 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 Caulfield 1, NJ1, blah, blah, blah. And I'd end up back in that only the key relationship again. The key to the office would identify both the work location and a mail stop in that case. So it's not in second normal form if I embed Caulfield and the key associated with it in here. Yeah.
So I guess what you're saying then is that NJ-1-C, that denotation is going to be enough to tell us that it is the Caulfield third column with mail stop ID, mail stop name, and then work location ID.
At this moment in time, it's enough to identify that. But like I said, if somebody comes in and they says, my kid comes in, fires me, Rob named all these buildings, I hate it, we're going to rename everything and purge his memory from the planet. Office 231 is still sitting down the hall with all sorts of garbage in it, just like I left it there. But we're going to name it something else. And because we're naming it something else, we want to change the name, but we don't necessarily want to change the key, because the key is spread everywhere throughout history around people who have been in that office and stuff like that. I could potentially have made work location ID NJ-1-C. And that could have been the key down here for work location ID for Caulfield. And then to your point, mail stop ID concatenated onto work location ID would have given me my fully qualified mail stop location. Could have done that. Nothing wrong with it. Just a matter of whether it fits your solution to the problem or not. And that's going to be the answer almost every time when you look at one of these types of scenarios is there's no right way to do this. There are some wrong ways to do it. And maybe the wrong way is the right way in certain situations. But there is no book of here's how you do data architecture and patterns and things like that beyond just making sure that your normalization strategy is appropriate for the problems that you're solving. Yes. Sure.
Keeping the mail stop ID constant.
Mhm.
Even if you change the data, keep the constant in place.
Correct. And that's the whole purpose of this is if I change an attribute, I should always hold the keys to be non-mutable.
So when you make it, never gets changed.
It should never change. Will never change is a hard to enforce promise, but you should operate off of the assumption that you will never change a primary key on a record. There will be some case at some point in time that will cause you to violate your tenet of thou shalt never change a primary key. I've done it before. It has happened. And here's examples of how it happens. How many digit is this mail stop ID? It's 5. We start making robots and we spawn off Skynet, and we got Terminators on every continent of the planet. And all of a sudden, we've got more than 99,999 mail stops. So now we have to go out and change the structure of that key, maybe to even be more useful than it is as just a big long number. So now we have to probably go back and modify all of the prior mail stop IDs that are out there. Take systems offline, stuff like that. It's just no fun doing it, but you have to do it from time to time. I've done it in recent history because somebody thought we would never, ever, ever have more than 100 billion rows of data in a table. Surprise. Yes, you can have more than 100 billion rows of data in a table, and it screws with every key in every table when you do it. So, like I said, you probably won't, but it's very possible that you will at some point in time. Mergers, acquisitions, things like that, especially. Any other questions? Hey,
We assign more than one primary key in a model.
can you assign more than one primary key in a model?
As an example.
So go ahead with your example.
Product ID
Yep.
is a primary key.
Mhm.
Customer ID is a primary key. Order ID is another primary key. Store ID is another primary key. So we can say all these are primary keys, right?
Every entity gets its own primary key.
Yeah.
Yep. Absolutely. Every entity gets its own primary key. You also have a concept, the book touches on it. We have a concept called an alternate key. Alternate keys typically are things that you would also index and search a record on. So in this case, my primary key is employee ID because it uniquely identifies a particular employee, but I may have alternate keys, which are the combination of last name, first name, and middle name. An alternate key doesn't necessarily have to be unique like a primary key does. So by using this set of alternate keys, I could potentially build an index into the table that efficiently allows me to find all employees named Reginald Eugene Smith. Now, it's probably going to return multiple employee IDs as a result of that, because there's probably multiple people named Reginald Eugene Smith over space and time. However, back to what we were talking about over here of having a mail stop ID and a working location down here, and embedding up combinations of location ID and mail stop ID, and then also having mail stop name. In this particular scenario, mail stop name is also unique because we've decided that NJ-1-C- always associates to Caulfield 1, right? So if I had the primary key from the location pulled up into this row, along with mail stop ID, the combination of mail stop ID is the same as the combination of location ID combined with mail stop name. So the combination of those two, or the concatenation of location ID and mail stop name, is just as unique of a primary key as mail stop ID in and of itself is. Because in Caulfield 1, there is only one mail stop name, NJ-1-C-231. So I could also use it as an alternate key, and in that case, it would be unique. So in that case, the table could potentially have two potential primary keys, but we would only refer to mail stop ID because it is the minimal number of values that can uniquely identify a row in this table. Is one more right than the other? Not really. Yes. So let me scroll this back up. The question is for work location ID. At this moment in time, we don't show that the primary key from the work locations table has been embedded as a foreign key into the work location mail stop table. If we were to do that, that foreign key in combination with mail stop name would have the same functional power of equivalency as the mail stop ID itself. So if you think about it in terms of math, F of 00231 is equivalent to G of 0001, which is the work location ID, comma, NJ-1-C-231. Those two functions will always produce an exact equivalency between the two of them. So in the fact that we don't show the work location ID in this table, we infer that it really is there because of this relationship line. So it's not so much that it's missing in the diagram, we just haven't explicitly expanded it out in this case. Now, why the difference between what we had before is that this ID was in the employee record, and that's what made it wrong. This mail stop name was in the employee record, and that's what made that wrong. So it's not that combining the ID from work locations into work locations mail stops is wrong. It's just that putting it into the employee domain was wrong. That you can get close to answering the question you asked. Okay. How many people are so confused at this point in time they want to just go home and drink? One? Be honest. Got to be honest. Okay. And that's absolutely normal. If you're sitting here going, my God, this is the most clear thing I've ever covered in my life, you need to seek help. Because until you've done this a handful of times, this is not things that normal human beings talk about and enjoy as favorite pastimes. And that's why I want to cover this stuff during this semester as part of learning how SQL statements work and learning how to create tables and learning how to figure out how to query data, because you almost never get a chance to fiddle with this kind of stuff in a job. You get lucky every so often and get brought in at the right part of a project where all of these conversations are being had and things like that, but most of the time you don't. And so this is a opportunity for us to kind of play with it and understand what it means to create a database as well as use a database at the same time. So that's my objective this semester is to get some hands-on practical experience doing this, because I guarantee you somebody's going to ask you a question on an interview at some point in time. And if you can go in there and just really start screwing with them with how much you know about everything up to Boyce Codd normal form, you'll earn some geek points for that. If they start addressing anything beyond Boyce Codd normal form, leave. You do not want to work there. Sure.
When you answered the last question, you said you haven't related the work location ID as foreign key to the main stuff, right?
I've done it in the diagram, but I have not physically embedded.
That's my question. When you use visual paradigm, it's asking you which attribute you would like to mark as foreign key.
Yep.
So you have to
So
you have to make relation.
notice there are no attributes in these tables at this point in time.
Yes.
That's why there's no attributes in these tables at this point. When you're doing logical data modeling, I try to avoid putting the actual attributes in the entities in the model as long as possible, because I'll change them and I'll fiddle around and I'll move them and I'll split them up, and I just don't even like the data type of this. And if I've already made that level of commitment of documenting all the attributes out, then when I go in and say, oh, wait a minute, I've made this key and I've selected this attribute as the foreign key value, and now it's embedded in the entity, I have to go back in and physically delete that attribute out of the child table if I want to change it, because just a matter of deleting this relationship will not necessarily remove the foreign key from the table. So I do it just strictly to prevent having to go back and undo choices that I've already made until I'm very comfortable with the entity layout. I'm lazy. That's the net. I'm lazy and I don't put entities in until I absolutely have to. So this logical is, in my opinion, just at the entity level with some relationship declarations as far as how things relate to each other. And I will create, these are nothing but text boxes with tables in them. I will create these text boxes with tables in them indicating the attributes and some example data for them, so that I've got some eye candy to work with while I'm dragging things around. But I haven't yet committed an actual attribute into an entity and that I have to end up making hard decisions on yet. And I, like I said, I just try to delay that process as long as I can. Because once you, another reason I don't do it, and this may be a me thing, once you start putting attributes inside of an entity, you kind of can't see the forest for the trees anymore. You get tied to what you've called a field or the data type that you've given a field or something like that. And it stops being about the big picture anymore, where you realize, wait a minute, I've got employees, and employees are really nothing but people, but now I've got my child has my employee ID embedded on his DNA now. How did this happen? If I stop working for big scary robots, do they go and harvest him? What happens? You know, putting attributes in there kind of starts to causing you to lose some of the bigger picture, causes me to start losing some of the bigger picture thoughts around things. So just like I said, everybody does it differently. That's just my way of doing it. Your mileage may vary. Let's see. So we're at third normal form. So help me God. Bill Kent, back in '83, in an episode of Communications of the ACM, kind of doctored this out because nobody had really put together this nice progression from unnormalized form of something just having a key to causing a dependency on the entire key and removing all of the partial functional dependencies that could potentially cause you to do a partial key update against a record, for example. So let's think about on our last example here with location. Let's say that we pull up our work location ID as a foreign key into this table here, the work location. God, it's unreadable, isn't it? Work location mail stops. So because this record now has both the foreign key and the primary key in it, I can potentially go through and do an update on work location mail stops using only work location ID potentially, and cause me to update more records than I intended to. That's called a partial key dependency in normalization strategy. By not using the entire key in this case, which is either mail stop ID or a combination of work location ID and mail stop ID, it's not necessarily obvious that I'm updating or modifying too many records, because nothing stops me from implementing an update statement just using work location ID. If this were an unkind system, it would come back and say, wait a minute, your update statement does not include a value for a primary key in it to assure that you're only updating a specific record or a specific set of records. Abort the operation. So when Kent put this together, everybody's eyes kind of went open pretty quickly because they started to understand, wait a minute, it's not just about picking the right primary key. And it's not just about creating a pretty data model that's appealing to the eye and allows you to tell a good story. It allows you to come up with a provable way of building a system that prevents you from accidentally modifying the wrong data in a given environment. You almost have to intentionally write a statement to screw the data up on a normalized system. So, like I said, we look at first, second, third normal form. Typically for analytical systems, we keep data in second normal form in general. And the reason we do that, like I said, analytical systems are read-only in general. So you don't have to worry about insert, update, and delete anomalies because they're read-only. The data is grouped together functionally in second normal form to support particular types of queries and reports that you want to run and print out. So concept of a database view. If I say database view, does that mean anything to any of you? Raise your hand if it does. So a view is basically, think of it as a query on one or more tables that allows you to put together a concatenation of data, either data that's aggregated in some way or data pulled from multiple different tables that puts it in one nice, clean little row set that's purpose designed to produce a report or fill out a screen on a user interface. Views, almost by definition, are second normal form. And by having those things pre-built and pre-structured, they're much, much more efficient than having to knit together 5 or 6 or 7 different tables to produce a report. So second normal form is probably what you strive to for more analytical purposes. Third normal form is what you strive to for online transaction processing systems, where you're constantly creating and modifying data in real time, typically a row at a time, a record at a time, a person at a time, a product at a time, something like that. The optimal batch size for an OLTP system is 1 record at a time. And you should index it that way. Beyond third normal form, and especially beyond voice cod normal form, the overhead of implementing the additional structures becomes ridiculous. So just as a quick study as to what that might look like, a 4th or 5th normal form table, every column or every attribute in a table would have its own table in the database with its own primary key. And this employee address, or this addresses table, would have an address ID for the specific address that I'm looking for. It would have a mailing address 1 ID that would go pull a street address out of a street address table and populate this particular column. Mailing address 2 would have an apartment or a building number or something else table that it would go and refer to pull a record out of. Cities would all have their own tables. States would all have their own tables. Countries would have their own tables. Postal codes would have their own tables. So every attribute gets its own table at that point in time. And from a performance perspective, in almost every situation, that causes major performance issues. And it also becomes very, very difficult for end users to write queries and application programmers to efficiently write code to use these kind of tables. I say almost every case. There is a class of database that has come out in the past couple of years called a column store database. And a column store database literally stores entire sets of columns as their own entities so that it can do massively parallel database lookups for analytics. They're an absolute pain in the neck to work with, but they allow you to take a query that would normally have to go out and pull entire rows of data, run queries against the entire rows of data, break those out into different parallel processes running on different servers, give you back the results, mesh back up what's called a bitmap result field to tell you how many of those rows actually ANDed together, produced a good result, and then the map, the reduce part of it, would actually go out and fetch all of the data and produce the result set for everything that got handed together correctly. People implement these things. They implement them for very, very, very specific purposes. They are not used broadly, but those are beyond fourth normal form databases. So when I say you'll never see them, you might see them, but you probably won't have to deal with them. And I don't think anybody would expect you to come walking in through the door having worked with a column store database before. I've worked with exactly 2 in the past 35 years. And they were for such wickedly ridiculous problems that I would never expect to work with them again unless I run into the same kind of problems that we implemented for them. Which brings us to Boyce Codd normal form. And this should be our last slide of the night. So early on, we were talking about the thing that didn't fit well. And traditionally, any entity that's in third normal form is also in Boyce Codd normal forms, except in the case where we end up with a non-obvious anomaly. So the first and most frequently violated contingent in this is zip codes change from time to time. We don't typically worry about it. When you put together a database of employee mailing addresses, you don't sit down and say, oh, dear God, everybody's got the same zip code. Let me pull it out into a separate table just in case the Postal Service ever changes a zip code for a particular address. But if you are a large enough enterprise and you have enough mailing addresses and enough people and enough different zip codes, and you've stored zip codes or postal codes throughout a lot of different records, it's very problematic to go back in after the fact and change a zip code and get it right everywhere, unless you've got all of your entities well documented, you've written and tested some really, really good queries, and you can take the system down for a period of time to make sure that nobody's going in and adding new erroneous zip codes for a city that changed 2 days ago. We get files from the Postal Service every so often that we reload in, and it goes out and it updates all of the zip code information when they change. So in big mailing operations, it's definitely an issue. So in this case, I might break mailing postal code out into a postal codes table. And let me see if I put this in as the slide or not. To fix this third normal form update anomaly. So this is a weird example because for each address that I have a mailing postal code, but that postal code entails a lot of information in and of itself. It entails the post office address that services that particular postal code. It entails the geographic region that postal code services at a given point in time. And it also entails the country that post office belongs to. We tend to think of United States postal system zip codes as being U.S. entities, but we have APOs and FPOs and stuff like that at different countries around the world. Ships have postal codes. Military bases in different countries have postal codes. And they're not always traditional postal codes that are served by a post office either. UNC Charlotte has its own postal code, 28223. It belongs to a building a campus up there for mail operations, and a postal service truck backs up there and dumps off sacks of mail, and they've got sorting rooms and people who look like postal service employees, and they do everything that postal service employees do, but they're property of the University of North Carolina at Charlotte. Bank of America has its own postal code, 28255 in Charlotte. They've got one in most large cities where they have offices. These are mailroom operations that are completely independent of the postal service, and they change from time to time. So just like the postal service making a change, Bank of America may stand up a new operation for what's the city up the road where the racetrack is, Concord. Maybe they stand up an operation in Concord and they get a new postal code, and or they stand up a new mailing operation, and now things that used to be served by 28255 now get served by 28 whatever the new post office is. So you have to go through and do those updates to specify that now all of these addresses are served by a whole new postal code. So when I did this in the table, I ended up using mailing postal code as my primary key for the postal code table, as opposed to a synthetic key. And the reason I did that was postal code 08096 won't in and of itself ever change. That post office will always exist in some way, shape, or form in history. It won't become 08097 or 08098. So the key value doesn't change. I might get a new one, an 08097, and some of these IDs may change. So the only reason I did this specifically this way was to identify that you don't always necessarily have to use a synthetic key for everything. And one could argue that postal code in and of itself is already a synthetic key. They just create a number that gets assigned to a particular location. So maybe postal code is in and of itself already a synthetic key. So questions?
We don't have any projects.
Absolutely.
What type of projects
I don't know. I'm making this shit up as I go along. So here's what I would think. As we start to build out big scary robots, and I'm sorry, I apologize. My language gets a little loose at night. If it bothers you, please let me know, and I will try to do my best to rein it in. Once we start building out big scary robots, that's where I would envision y'all start working as teams on that. And the rationale behind it is kind of like I said, a lot of this is bring a friend with you. When we design databases at work, we very seldom do it in isolation. And it's not because we can't do it in isolation. It's the little things you forget, or the assumptions you make, or things like that. And it's nice to have somebody sitting there across the table from you saying, yeah, but what about the case where blah, blah, blah could happen? Quite frankly, I didn't even think about the whole your child could become an employee thing until I was sitting down at Einstein Bagels right before class. Whereas if I'd had somebody else working with me, probably would have found that out last week. So it's always better to do this with a friend, to help get past assumptions and things like that. It's also better to have a friend who isn't your normal friend, but somebody you know as an acquaintance somewhere else in the building. When I was at Ruby Tuesday eons ago, we were replacing our old mainframe accounting and HR system with a first generation client server ERP system. And we defrosted all the old guys in the freezer and brought them out and got them to help us figure out things that had happened over the last 30 years to make sure we didn't get caught by surprise with anything. It was kind of funny. Somebody be saying, yeah, and every 7 years, blah, blah, blah happens on July 22nd. You mean, where did every 7 years come on? Well, it just kind of happened that way, and it's hard coded in there, and it's been doing blah, 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 and we can't change it. What do you mean we can't change it? Oh, we'll get fined $5 million by the IRS if we change blah, blah, blah. You can't do it. Whatever you build is going to have to do it. Really? That's awesome. Any other tricks? No, I can't really think of them. Oh, remember that thing Joe did? And every so often it does this. And so maybe it's also a good thing to widen out your group of friends, putting these project teams together as well. I think Yusuf, you had sent me an email asking about maximum team size. Yeah. So let's see. I think we've got on the order of 28 people in this class. I'm not sure how many people have dropped over the past couple of weeks after hearing me drone on about stuff, but I don't have a problem with the team being up to 6. Like I said, the purpose of assignments in this class is to give you opportunities to play with things and do things, not just try to crank out an assignment that's pretty and, you know, matches all of the goals and everything else and looks like a textbook thing you could download off the internet. The whole purpose of this is to get your hands dirty, you know, slam your knuckles in the doors a few times by accident, and to get a good feeling of how to use these techniques by the end of the semester. Nobody's going to ask you for your deliverables from a programming course in college at some point in the future. But if you can come in with that one unique little gem of knowledge that you picked up somewhere from playing, you know, that's what you're doing this for. So, you know, if y'all want to put together a 6-person team, that's fine. If one of y'all wants to just lone wolf it and do it by yourself, I'm fine with that too. Just understand that if you try to take this on by yourself, you run the risk of not necessarily learning as much from the course as you could have. That's the only caveat to that. I always did assignments by myself, and that was probably the single biggest downfall of that was I didn't have somebody sitting there pointing at me. Well, that was a stupid decision. Why did you do that? So just think about it from that perspective. All righty. That's the material for tonight. So I we've got a chat message out there. Hi, Allison. So the main assignment that I put out there was to install MariaDB on Docker. I put a module on the main page that kind of discussed installing Docker on your system. The second one is downloading the MariaDB. Can't talk anymore. Downloading the MariaDB module and creating a container from it on your machine. It should be pretty straightforward to get that done. And I'm going to put some additional information out there over the next day or so to help out with it. But it should be pretty straightforward to make Docker run on your computers. And it should be pretty straightforward to create a container from the MariaDB download. I'll put some specifics out there around that, just to kind of help you track through it. And the deliverable from it is nothing but screenshots of going through getting MariaDB working in a container under Docker. So it's not a crazy assignment, but I think it will make it easier on you trying to get MariaDB and some of the other tools that we're using to run, instead of trying to install all the individual components and getting them tuned and stuff like that. So that's kind of the direction out of that. I know a lot of people ask in job interviews, have you ever done anything with Docker or Kubernetes or anything like that? And being able to say, yeah, I did X with it with MariaDB. Half of them are going to ask, what the hell's MariaDB? And the other half are going to ask why. So Rob said, all right. Yeah.
Technical, the Docker, MariaDB, and so on and so forth. Very technical actually for developers.
Yeah.
Someone like me who's not coming from computer science or developing field.
So, oh yeah, absolutely. And I'm gonna try to make that a little more available to you to do that with, because let's be honest, installing a database system on a computer is typically reserved for sysadmins and database administrators and stuff like that. So MariaDB is pretty forgiving in terms of just getting it running on a computer. That's why I picked it versus some of the other technologies that we could have played with. But it also has all of the features of a full-fledged database system. You know, I wanted to do Microsoft SQL Server, but Microsoft SQL Server runs on Linux and it runs on Windows, but it doesn't run on Mac. MariaDB is one of the few that is pretty much directly SQL compatible with SQL Server and Oracle, but will run on Linux and Windows and Mac. So once you get it installed, and you can connect to it, we're going to create a database on it. And then we're going to start creating tables using Visual Paradigm into the forward engineering your Visual Paradigm documents into MariaDB. Probably do a few hand created tables, create table, blah, 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 such and such, just to get a feel for it. I used to, back when I really cared, all of my guys, I wouldn't give them any graphical tools at all until they had passed all their certification exams. And you had to do everything from the command line. And by God, they passed their cert exams really quickly because of that. But you know, in today's age, most of the tools for most database systems are graphical. There isn't even a command line in a lot of cases. So I can't really make y'all do everything from command line in here. Any other questions?
So MariaDB is similar to SQL, right?
Almost identical. It is a public domain community version of MySQL after Oracle bought it, basically is what it is. So anything you can do in MySQL, you can directly do in MariaDB. But also a lot of the stuff that you can do in either Oracle or MySQL, or excuse me, Oracle or Microsoft SQL Server, you can also do directly in MariaDB. So it's actually quite a nice database platform, and there's also an enterprise version of it that you can, you know, install on clusters and run full-scale enterprise loads on. We're not going to get into any of that in here, but it is a capable tool of doing that. Any other questions? Okay. Y'all have a good night. Good seeing y'all again. Thanks.
Thank you.